Okay, so how do we graph an exponential function in a transformed form? So we have y equals a times b to the exponent, k x minus d, and then plus c at the end. So one of the things you want to think about is what the base graph is actually going to look at. So let's say you had an example like y equals, and I'll just make one example up. So let's say you had y equals -2, and then 3, 2 bracket x minus 1, and then plus 1. So let's say that's the function you were given. Now it's very easy to get confused and say, okay, there's numbers everywhere, what represents what? But if you understand that the number that has the exponent applied to it is actually the base function, it's very easy to actually see what your base graph is. So I'm going to highlight the base that actually has the exponent applied to it. So that'll help me remember that this is not actually a transformation. That is actually the base function. So for this example here, the first thing I would do is determine the base graph, which in this case would be y equals 3 to the exponent x. So in this case, I would have y equals 3 to the exponent x. Now, all the other numbers that you see in this equation are all the different transformations that are applied to the graph of y equals 3 to the exponent x. Okay? So this is one example of an exponential function with transformations applied to it. Now, you could have had a different base, and you'll see that in the examples that we're about to do. You could have had a different base as well. And again, highlight the base function. So highlight the value that has the exponent applied to it. So in this case, it's a 3. And that'll tell you that that's the base graph. The second thing I need to do once I figure out what my base graph actually was is to determine what the key points of this particular base graph is. Okay? So it is possible for you to have multiple different base graphs in exponential functions. So the difference here is that there is not necessarily one set of key points and then all the transformations are applied to that. Each different base function has different key points. Okay? So for example, if you had y equals 2 to the exponent x as your base function, this function would have a separate set of key points in comparison to the base graph of y equals 3 to the exponent x. They have different bases, the graphs will be different, so that means their key points will also be different. Okay? So for exponential functions, that's the additional thing that we do need to look at. It's figuring out what the base function is and then determining key points based on the base graph. Okay? Now if we think back to exponential functions, remember that the base graph will either increase or decrease depending on what the value of the base is. So let's take a look at this graph again. Okay? So depending on what the value of the base is, we're either going to expect an increasing graph or a decreasing graph. And this can change depending on the different transformations we might have applied to it. But what we want to think about is what the shape of the curve is going to look like. Okay? So I chose specific values of x, and based on those values of x, we can find corresponding values of y. So the values of x I chose are -1, 0, and 1. And based on those three values of x, you should be able to get the curvature of the graph. Okay? And so, going back to our key points here, let's say that our base function was y equals 3 to the exponent x. What that means is I need to solve for when x is equal to -1, x is equal to 0, and x is equal to 1. Okay, so let's say we had y equals 3 to the exponent x. This is just an example. This is not always the case. Then I would need to solve for y equals 3 to the exponent -1, which I know is 1/3. And I'm not sure if you can see that, but that says 1/3. And then I can do the same thing for 3 to the exponent 0. And I know that any base and exponent of 0 is equal to 1. And that makes sense because the y-intercept for all base exponential functions are 0 and 1. And then I can do the same thing for the last one. So that's 3 to the exponent 1. And that gives me y value of 3. So there's an example of a set of key points for a base function of y equals 3 to the exponent x. Now the rest of your work is exactly the same as what you've seen all along. You can apply the transformations on the x value and on the y value to get your new points. But what you also want to remember is that your graph has an asymptote. It has a horizontal asymptote, which is normally at y equal to 0. But as you shift the graph up and down, based on the value of c, the actual horizontal asymptote will also move with it. So for example, in the random example that I made here, I know that if I had an exponential function and I shifted the graph up 1 unit, what would happen is the asymptote would move up 1 unit as well. So for this graph, I know that the asymptote would have moved to y equals 1. Okay? And that value of 1 comes from the value of c in the function that was given. Okay? Just an example, not necessarily the one that you'll always see, but just an idea of what you can look out for. So once I know where the horizontal asymptote is, and once I use the mapping formulas to find the transformed points, I can plot the points, and now I would sketch a curve that approaches the asymptote on one side, and then the other end will either approach positive infinity or negative infinity, depending on which direction the graph is going. So just to remind you again, one end of the graph you're going to expect to approach the asymptote, so it's going to get closer and closer to the asymptote. And the other end of the graph is going to move away from the asymptote, either approaching positive or negative infinity. And that's what we can expect to see, and we'll see that in some of the examples that we are about to look at.